is Igor Khavkine from Prague, and it's time to begin. So, Igor, you're welcome. Please share. Oh, okay.
Hi, can you hear me?
Yes.
Yes, and I hope you can see my screen as well.
Yes.
So thank you very much to Joseph and the organizers of this seminar. I'm very happy to be back to talk about some recent work. Well, recent, you can see from the references here, the most recent contribution appeared already on the arXiv last year, but it's still in the very slow process of publication. So it hasn't appeared anywhere else yet. So the title of my talk is a little bit long, and it relies on, so the topic itself relies on some motivations from studying linearized gravity, linearized Einstein equations on the background of a spherically symmetric Schwarzschild black hole. But I'm not going to spend so much time on these background and motivational issues. I'm going to talk more about just kind of pure differential equation issues, algebra, geometry of differential equations, which might be of interest to this audience. So let me first start by showing you a model problem that basically tells you the kind of things that I would like to study and to achieve. And I have to start by explaining just a tiny bit of the geometrical setup. So we're working on a Lorentzian manifold. So it's a smooth four-dimensional manifold that has a metric of Lorentzian signature. And you can see the metric written explicitly here in coordinates, which you can interpret as time, radial coordinate, and theta phi, sorry, this should be phi, spherical coordinates in 3 dimensions. This metric has this particular function, which identifies as specifically the Schwarzschild geometry, which looks like this. It happens to go to identity for large values of R. And you will see that in that limit, this metric approaches the metric of flat space, or Minkowski space, as you will. And another limit, when R is equal to 2m, this function is equal to 0. And it so happens that the metric degenerates at that value of R. And it's, well, that's just a coordinate artifact, an artifact of the coordinates that were picked here. And that location corresponds to the so-called horizon of the black hole. So we're mostly interested in the interval between R equals to m, the horizon, and R equals infinity. So this is the external region of the black hole. All right. So what do we want to do on this geometry? Well, what we want to do is we want to solve using separation of variables the wave equation. I'm not going to write the wave equation here. I think it's pretty clear how to get it from this metric, right? So it's the Lorentzian signature analog of the Laplacian corresponding to that metric. And because the metric has multiple symmetries, like it's static, so the components of it don't explicitly depend on time coordinate, and it's spherically symmetric, you can do some pretty standard separation of variables, right? So introduce time harmonic modes, spherical harmonics, factor out R dependence for each for these particular frequency and angular momentum modes. And if you plug this separated ansatz into the wave equation, what you find is the so-called radial mode equation, okay, for these radial modes. I will refer to a certain family of ordinary differential operators that depend on the variable r as d subscript s. And so what appears here is d, so-called d0 operator. This family is known as the family of Regge-Wheeler operators, named for the people who first kind of wrote them down in this context. And they have the quite simple explicit form that you see here. Okay, so there's a kinetic term, there's a potential term, and then there's a term that has the spectral parameter, which is the frequency squared here. And if you take all of these terms into account, you get a pretty standard equation of Sturm-Liouville type. As you also see that it's formally self-adjoint. Right. So the radial mode equation for the scalar wave equation happens to be the Regge-Wheeler operator with S parameter called spin parameter equal to 0. And later on, we will encounter these operators for spin values 1 and 2 as well, right? So, but for now, keeping in mind that this is a kind of a standard Sturm-Liouville type operator, what can we conclude? We can conclude that it defines a self-adjoint spectral problem for the spectral parameter omega squared. This spectral problem is defined on a particular function space. So the function space is an L2 space with a weight which is determined by one of the coefficients of this equation, right? It's nice and positive. Also the potential that appears in this equation is also positive for the values of S that interest us, and some simple limitation restricting the values of L and S for which this potential is in fact positive. And because of that, we can conclude that the spectrum of this equation for omega squared is real. So the spectrum is contained on a half real line from 0 to plus infinity. And it means that when we consider frequencies that belong to the spectrum and plug them into the time harmonic modes, we do not get any exponentially growing or decreasing solutions. So the time harmonic modes for frequencies that belong to the spectrum are purely real. Okay, so this is very nice. So it has some applications in theoretical physics, which I'm not going to get into, but this is something that we would like to have for this and other equations, or if it's not satisfied, we would like to know whether that's the case or not. Okay, and another convenient thing that we get from just by the standard form of the equations of this equation is that it possesses a complete orthogonal set of generalized eigenmodes, right? So since the spectrum is continuous, there's a continuum of eigenmodes indexed by the frequency parameter, but they satisfy a generalized orthogonality condition a la Fourier modes. Okay. So any questions so far about this model, what I consider to be the model problem? Okay. All right. So maybe no questions, but if you do have any questions, feel free to just interrupt me during the talk. Okay. All right. So now I want to, in a moment, I will move on to more complicated equations. So these will be tensor wave equations on the same geometry. Okay, but before I do, I want to just state a pretty straightforward lemma. Right? So suppose that I have a differential operator. It's still an ordinary differential operator, depending on the radial variable. It's a matrix differential operator. In this case, I chose it 7 by 7. So this is on purpose because it matches the structure of one of the operators we'll see later on in this talk. But it could be pretty much any triangular operator with similar structure. So on the diagonal here, we have Reggie-Wheeler operators of different spin parameters. Okay, and I'm not indicating exactly what they are, but we have some off-diagonal terms which appear only above the diagonal, right? So this is in triangular, upper triangular form. And if it so happens that these off-diagonal terms are, there's a technical word for it, relatively bounded with respect to the diagonal operators that appear here. So formally, I mean, you have to introduce a bit more notation to define this, but you could basically just say that what's important is that the inverse of one of the diagonal operators multiplied by one of the off-diagonal ones should be bounded in the functional sense that we're talking about here. All right, so if that condition of relative boundedness and upper triangular form is satisfied, then considering this as this operator as depending on omega, you know, through the diagonal terms here, it has the same spectral properties as its diagonal terms. Okay, and this is a pretty standard result from finite dimensional linear algebra. Here we're dealing with infinite dimensional cases, but the only hypothesis that we need to deal with the infinite dimensionality is this relative boundedness hypothesis. Okay, so how do we prove this? Well, basically we need to compute the resolvent. So basically take the inverse of this and notice how it depends on the spectral parameter omega or omega squared. And since the inverse of this upper triangular matrix is going to be polynomial in the diagonals, and the diagonal terms multiplied by the off-diagonal ones in this way, then if there is some spectral value, some value of omega or omega squared that appears in the spectrum of DSs, then it appears in the spectrum of this upper triangular operator and vice versa. Okay, so the spectral properties of such an upper triangular operator are determined fully by the diagonal ones and have the same nice properties that we already saw on the previous slide. All right, how does that help us? Well, it would help us if we were studying these two particular tensor wave equations, so a wave equation on vector fields, and so-called Lishnerovitz wave equation on symmetric two tensors, which appears in a particular way when we linearize, when we gauge fix the linearized Einstein equations in a particular way. Okay, and in fact, the vector wave equation also appears as a kind of gauge fixing corresponding to Maxwell's equations. All right, so if we were to take these equations on a Schwarzschild geometry, apply separation of variables, get their radial mode equations, and if their radial mode equations were in this triangular form, then we would be done, and we will basically know everything we wanted to know about their spectral properties, which basically should be the same as these nice spectral properties of the that we discovered for the scalar wave equation. All right. Now, is this true? Okay, is it the case that when we do separation of variables for these equations, that we get the nice upper triangular form? Well, unfortunately, this is not true because I will show you the explicit form of the radial mode equations that we get, and you will see that they're definitely not in upper triangular form. So in fact, some of them can look quite scary. So there's some technical thing that allows us to separate the modes into two sectors, the odd and even sectors. Odd sector is usually simpler, and the two sectors are decoupled from each other. So I always present the radial mode equation separately for each sector. So there are 4 components for a vector field in 4 dimensions. This is of course, so I get 1 by 1 odd subsector and a 3 by 3 even subsector. And well, so this equation actually is pretty much in Sturm-Liouville form, but this 3 by 3 system is definitely not in this desired upper triangular form. Okay, and kind of looks complicated, so it's not clear what we can do with it without having this upper triangular form to work with. And if you apply separation of variables for this Lishnerovitz wave equation, so the symmetric 2 tensors split into 10 independent components, 3 odd ones and 7 even ones. So for the 3 odd components, the system again does not look anything like upper triangular. And in its full beauty, the 7 by 7 even subsystem of the Lishnerovitz wave equation again does not look anything like it's an upper triangular form. Okay, however, so what I will do is I'll show you the final result of my work, and then we'll go through some details of it. Okay, so the final result of the work is that for both the vector wave equation and the Lishnerovitz wave equation, we can in fact simplify the complicated equations I showed you before. So they're radial mode equations in their original forms. We can simplify them to upper triangular forms with Reggie-Wheeler operators on the diagonals. Okay, and sparse upper, so off diagonal terms, which happened, so I won't tell you exactly what you need to check it, but you can take my word for it in the stock, that they happen to be relatively bounded with respect to the diagonals. So we can apply that triangular lemma that I showed to you on the previous slide to these equations. Right. So the final result of the works that I'm talking about here is that yes, you can simplify the radial mode equations from their original complicated form to these nice sparse upper triangular forms with Reggie-Wheeler operators on the diagonal. All right, so that's the main punchline of the work that I'm describing here. Okay, any questions at this point? Okay, so if not, then I will move on. All right, now, how do we actually achieve this simplification? Okay, I have to tell you what the simplification means and how which strategy you can actually follow to achieve it. Okay, so let's take one of the more complicated operators. So in fact, the more complicated operator, which is the Lishnerovitz radial mode operator, say in even sector. Well, it so happens that there's some nice geometric structure to this equation. Okay, so you might recall that the Lishnerovitz wave equations is a kind of wave operator or Laplacian in more general Riemannian, pseudo-Riemannian sense. And it obeys some nice identities with respect to other natural operators that appear on the Riemannian manifold, like taking derivatives, gradients, divergences, and so on. And you might know or recall from Euclidean space that the Laplacian for just flat space satisfies some nice identities with respect to the derivatives. So it basically commutes with a normal derivative, and you can use this commutation to again take divergences, gradients, and so on, and commutes nicely with the Laplacian. Okay, So if you take corresponding identities on the Schwarzschild background, it so happens that you can use such identities, and I'll describe in more detail how you can use them, to come up with a hierarchy of degrees of freedom. So before we just had like all the degrees of freedom, which we didn't really know how to split into different pieces. But these identities tell us that they can be split into 3 groups, which can, and this information can be used to come up with an equivalent form of the original equation, which now has triangular form. Okay, and the operators on the diagonal of this triangular form have to do with the hierarchical separation of the degrees of freedom that I just mentioned. Okay, so this step allows us to go from a complicated, dense form to this upper triangular block form. Okay, so in principle, each one of these could be a non-trivial block as well, and then we can try to apply a similar strategy recursively. So each block which is not yet 1 by 1, we can simplify again. And it so happens that the blocks that we had obtained were themselves so going from the Lichnerowitz wave equation, we go to blocks that look like vector wave equation, and already 1 by 1 Reggie Wheeler block. Okay, so the vector wave equation blocks we simplify once more. Okay, so each of the vector wave equation blocks becomes one of these 3 by 3 subblocks, and so that introduces some more off-diagonal couplings. But the diagonals are now already 1 by 1, and they are in these Reggie Wheeler form. Okay, very good. The next step is to try to simplify the upper triangular part as much as possible. In particular, this is necessary because some naive way that we might arrive at this could generate very complicated expressions off diagonal, and they might not be relatively bounded, which is one of the desiderata that I expressed on previous slides. Okay, so the next step in the general strategy is to basically try to set to 0 as many of these off-diagonal components as possible. And for those that cannot be set to 0, try to simplify them to a form that makes them relatively bounded. Okay, and what is it that I mean by equivalence? So all these steps somehow should not lose any information about the original equation. And to make that precise, I basically refer to, I speak of equivalences in a sense of the category of linear rational differential equations, which I think might be familiar to some of the people here from the Vinogradov school. Or equivalently can be phrased in terms of D modules, but I'm not going to go into that direction. Okay. So this is the general strategy that one can try to follow. Of course, along the way, there might be some obstacles, and maybe you get to a step which you would like to complete, but you cannot. And there are a couple of steps like that in this strategy. It so happens that whenever you do one of these triangular reductions, it takes a bit of work to make sure that this left upper block has the nice final form that I show here. And the reason that it does so in a Schwarzschild spacetime is what I consider to be a kind of minor miracle. And I don't know, maybe people who study integrable systems might be able to pinpoint exactly why that miracle occurs here. but I just ascribe it to the special nature of the Schwarzschild geometry that we're studying here. Okay, so that's the general strategy that goes from the complicated original equations to the final simplified form that I already showed to you. And so now I'll talk about some of the details, but maybe in reverse order, reversing the order that I just presented them to you in, because I think it might be easier for the audience to interpret it. Again, before moving on, so any questions? All right, okay, let me continue. Okay, so what is the first detail that I want to talk about? This is the precise notion of what does it mean for two equations to be equivalent in this categorical or D-module sense. And more generally, what does it mean to have a morphism between two equations? Well, usually when people study differential equations, they consider operations that map solutions to solutions as nice kind of transformations between differential equations. So this is what we try to codify as a morphism. But taken as a kind of a naked definition, this is not so useful. So what I will take as a definition is a bit more structured. And this extra structure allows you to, of course, prove more things about morphisms and equivalences. All right. So the basic objects that we're talking about here are differential operators. And you can kind of keep the discussion at the just general level of linear differential operators. But I will only need for the rest of the work to consider ordinary differential operators, and in fact, ordinary differential operators with rational coefficients. So at some points, you might notice that I might say something which only applies in this more special case, but I think a lot of, at least what's on this slide, applies generally to linear differential equations. All right, so I will, when speaking of a differential equation, I will interchangeably refer to the equation or to the operator as the equation itself. And the first kind of maybe non-obvious thing that you can do is replace or generalize the notion of an equation or an operator to a complex of differential operators. Okay, a complex is a sequence of differential operators that compose to zero. And of course, the Drum sequence in differential geometry is maybe the most famous example of that idea. Besides the original operator, the subsequent ones in terms of the theory of differential equations could be interpreted as Noether identities, or Noether identities among Noether identities, and so on and so forth. Because the complexes that we're dealing with are typically of finite length, you can, as you wish, you can extend them to infinite length by appending zero maps at the beginning, at the end. But this is just notation, so we don't always need to explicitly write it. And once you interpret an equation as a complex, okay, and if you have an equation that is determined, doesn't have any Noether identities, it will just correspond to one single operator. Okay, you can recover the notion of solutions through the idea of cohomology, which is a natural object associated to a complex. So I think probably a lot of people in the audience are familiar with ideas from homological algebra, so I won't really dwell on that so much. But basically, the solutions of the original equation could be thought of as the cohomology in this slot where the original operator is applied to. Okay. Also, if you consider cohomology in the target slot here, in target node of the complex, it corresponds to the co-kernel of the original operator. Of course, these are what becomes more complicated if it's extended by non-zero Noether identities. Okay. Once you have two complexes of differential operators, a natural notion of morphism between them is what's sometimes called a cochain map. So it's a ladder of differential operators that map between the two complexes such that all the squares commute. So the composition of E post-composed with K prime has to equal K post-composed with E tilde here, and the same for all the boxes. So that's what it means for the for this diagram to be commutative. And once you take this commutativity as an axiom, then this desired property that the morphism between differential equations will map solutions to solutions is a simple consequence. So it's just a matter of following the arrows here in this diagram and decoding the commutativity of the diagram. Okay, then there's a notion of homotopy, which is denoted here by these dotted arrows. So it's a ladder of operators that kind of go backwards by one in between the two complexes. And whenever you have a homotopy between two complexes, you can use it to induce a chain map by basically composing this trapezoid, composing operators in this trapezoid like this. So add this composition with that composition, you get this formula. And it so happens that for any choice of the H's of this type, the induced K's are create a commutative diagram. Okay, and it's also convenient to consider those morphisms that are induced by a homotopy to be trivial in a certain way, and which induces an equivalence relation on morphisms between differential equations. Okay, and if you want to define an equivalence in this sense, then an equivalence between two complexes is basically a set of chain maps that go in one direction and also the other, so that if you compose them, you get a morphism from one of the complexes to itself, which is up to homotopy equivalent to the identity map. Okay, one can kind of decode this by writing out all the identities explicitly. But if you go to the case where the complex is just of length 1, it just has one operator without any Noether identities, then an equivalence is summarized by a diagram of this form, and this composition of the K with K tilde being inverse up to homotopy is basically becomes equivalent to the composition of the K and K bar operators is they're inverse to each other on solutions. Okay, on the cohomology of this operator. Okay, but we are not going to talk much about the cohomology because we're not going to really choose any specific function spaces most of the time that these operators act on, and just work with the identities between the operators and morphisms between them, homotopies, and so on and so forth. All right, so this is the formal notion of equivalence between two differential equations in this sense. It could be between a complex or just a single equation. Mostly we will see just single equations, but there's one particular place where you need the longer to apply it to longer complexes, which is why I introduced the general notion. Okay,
Igor, do you require this thing to be resolution? Because if if you just want one equation determined by E, then this complex should be resolution for this to be equivalent to usual.
Right. So I don't require it to be a resolution, but of course, in many cases, you want to have a resolution, you know, to to avoid some.
And then, and am I right that if it is the resolution, then it is exactly the same story as we do in if you do like BV for non-gauge system, you get Koszul differential, and it is just a reformulation of it in terms of different underlying differential operators.
Yes, more or less. So it's just that in that case, I think you have to. So when you start with some differential operator, you can, if it's sufficiently regular, you can define morphisms to just be differential operators that map solutions to solutions. And you can build these complexes by doing exactly these resolutions, as you say. But they need to satisfy some regularity hypothesis. So I just presume that all of this whole ladder of operators exists from the beginning.
But anyway, this notion of equivalence is the same as more or less the same. I don't understand technicalities, of course. There's a notion of equivalence for gauge system in terms of differentials, right?
Yes, yeah, because the differentials that you're talking about, these BV or Koszul differentials, they kind of encode the entire complex in it.
Thank you.
Yeah. Okay, so. Now, again, remind you, we're going in the reverse order compared to the steps that I described to you before. So now I'm going to talk about the simplification or a reduction of an upper triangular system, which means trying to, so a reduction in the same sense as, in representation theory, you can have reducible modules, reducible representation, and so on. So basically, starting with an upper triangular system, I want to try to cancel some of the off-diagonal terms by using equivalences. Okay, so suppose I have a block upper triangular operator in this form. Okay, it has some off-diagonal block, and I'm asking the question: does there exist some equivalence that maps this operator into this one? It has the same diagonal blocks, but the off-diagonal block is now 0. Okay, so keeping the triangular form, you can kind of make an ansatz for what the equivalence morphisms would be. So I write them only in one direction because it's pretty easy to come up with the inverse, right? You just put the minus signs in the off-diagonal terms here, and the commutativity of this diagram, which basically tells you that these matrix operators constitute a morphism. Once it's written out fully, basically it comes down to the following operator identity. Okay, what you want to do to simplify this, to achieve this simplification, what you need to do is to solve this operator equation. So E0, E1 are fixed. Okay, so for us, there are just going to be some determined ordinary differential equations. And you have this delta, which is sitting in this formula, and you want to find big delta, and you want to find the small delta and small epsilon, which together, when you do all the compositions, satisfy this equation, right? So if this equation is satisfied, then you put these delta and epsilons here, then you can achieve the reduction of this upper triangular system to a diagonal decoupled system. Okay, that's great. There is an obvious generalization of this to upper triangular systems of any size. So it could be many blocks. So they don't have to be just 2 by 2. I think it's quite easy to see. So the main question is basically, how do we solve this equation, which I marked by star. Okay, and it's possible that sometimes for particular delta there is no solution, right? So such a system would be irreducible in some sense. But if it is irreducible, I mean, you could still choose some non-trivial delta and epsilon to maybe not to cancel this big delta completely, but to simplify it in some sense, right? So I talked before about off-diagonal elements in these operator matrices that we're dealing with, that they should be relatively bounded. Well, maybe you would want to choose a representative for delta to make it relatively bounded if it was not before. Okay, so how would you answer these questions for specific choices of E0 and E1, which for us will be these Reggie-Wheeler operators for different spin values. Okay, so recall that these are second-order ordinary differential operators in the variable R. I won't go into details here, but I think it's not hard to believe that you can reduce the equation star to the case where the little delta, little epsilon, big delta are all at most first-order ordinary differential operators. Okay. Let me parameterize these first-order ordinary differential operators in some particular way. Now, I could have just written, delta 0 plus delta 1 times derivative with respect to R as parameters, but turns out that that choice of parameters is not so convenient. Okay. So I choose slightly different parameterization, but what's important is that they're just independent parameters in front of the derivative and the zero somewhere in the zero order term for the big delta, as well as for the small delta, right? So this is achieved by these plus and minus components. And it so happens that once you have parameterized the big and small delta, then the epsilon is automatically fixed somehow by the structure of the operator equation that we're trying to solve. Right. So if I use this parameterization, I just do the compositions, right, and figure out what are the and then I set equal both sides order by order, right? So I can expand both sides in derivatives with respect to R with some coefficients, and I set the coefficients of the corresponding derivative order to be equal on both sides. So once I do that, I obtain a differential equation on the little deltas, okay, with a right-hand side given by the big deltas. The original equations had rational coefficients, okay. The equation I obtained here, I don't write it fully because it's a little bit long, but it also has rational coefficients. One motivation for choosing this kind of complicated parameterization is so happens that this equation that I obtained here happens to be self-adjoint, which exploits the self-adjointness of the original Reggie-Wheeler operators. Okay, so it is just some nice technicalities, but the point is that I reduce this operator equation to a rational ordinary differential equation on some parameters with some fixed right-hand side. Okay, so the question becomes to be able to set these deltas to 0, or cannot be set to 0 to choose the optimal representatives, is basically to analyze the kernel and the co-kernel of this rational differential operator in rational functions. Okay, I'm sticking to rational functions here and transformations that have rational coefficients, just because if you leave that world, then it's extremely difficult to do any explicit calculations. And even if you do come up with a way to do these simplifications and decouplings using non-rational transformations, then probably not so many people will use them and pay attention to them. Okay, so now we have reduced this part of our work to analyzing the kernel and the co-kernel of a rational ODE in rational functions. Well, it turns out that this is a quite kind of old topic, and there's quite a bit of literature about this. And I was able to take advantage of that and add a little bit to it. So maybe not something which is completely new, but not, as far as I could see, not really used in the context where I was trying to apply this theory. Okay, so what is the main observation that allows you to do to even get close to analyzing the kernel and co-kernel of a rational ODE? Well, if we're looking at a rational function, it has a kind of canonical form in terms of partial fractions, and has a finite partial fraction decomposition, and each term in the partial fraction has a particular pole, a pole location, and so on. There are finitely many of them. Well, it turns out that if you look at a rational ODE with a rational right-hand side, then if you look for rational solutions, then the poles, the location of the poles of the rational solution are actually determined by the location of the poles of the right-hand side, and also of the location of the singular points in kind of in the sense of Frobenius of the equation you're trying to solve. Right. So if you know where the poles of the right-hand side are, and you know what the singular points of the linear rational equation that you're trying to solve are, then you basically, what you can do is you can come up with a universal denominator for a potential solution here. Okay. So this denominator will be polynomial, and it will just contain sufficiently many factors to cover all the possible poles that you need of necessary degrees that you need. Okay, and the Frobenius method will also tell you what are, using critical exponents, what are the bounds on the poles at any particular location. Okay, and in particular, once you use this this universal denominator, okay, and write your ansatz, your rational ansatz, as a numerator, which you could say just polynomial or in R, or more generally Laurent polynomial in R, with this denominator. Then the Frobenius method tells you bounds on the maximal order of the pole of this coefficient at 0 and at infinity. And basically what that tells you is that this denominator can only be a Laurent polynomial of bounded upper and lower orders. And that just means that, you have reduced the search space for the potential solution to a finite dimensional space. Okay, very nice. So this this result is can be summarized in this useful lemma. So if you have a rational ODE that is acting on the space of Laurent series of particular types. So there are different types that we should consider. There are those that have to do with basically this coefficient here. Sorry, this numerator, which are just finite order Laurent polynomials. But it's also useful to consider semi-bounded Laurent series. So those that have orders bounded from below or orders bounded from above. And it is also important to consider fully unbounded Laurent series. Okay, and in each case, the differential operator that we're dealing with should be compatible. So it should be possible to act with it on the corresponding space. So for example, if you want to act on the space of Laurent, unbounded Laurent series, then the coefficients of E must be bounded Laurent polynomials. Otherwise, you don't get the appropriate finiteness properties on multiplying series by series. All right. So it turns out that using these ideas, you can prove that the kernel of the rational ODE that we want to consider is finite dimensional in each of these spaces. And so there's some nice literature by Abramov and many collaborators starting already back in the 80s, maybe even earlier, and going up till today that cover mostly these three cases. And I had to kind of cover myself the case of the unbounded Laurent series, which somehow I couldn't find in literature. Right, so this kernel is finite dimensional, and now I want to also be able to say something about the co-kernel, right? So I have found much less literature about the co-kernel, so I had to come up with some idea of how to deal with it myself. So my idea was to basically to consider the residue pairing between Laurent series. Okay, the residue pairing basically, takes the product of the two arguments and takes the coefficient of the power of the r minus to the -1 term. Okay, which if the series converges coincides with the usual residue definition by using a contour integral. Well, this residue pairing is quite nice. It's defined on compatible, what I call compatible pairs of particular Laurent series types that you can see here. In particular, the unbounded Laurent series forms a compatible pair with bounded Laurent polynomials. This pairing has a nice property that taking adjoints with respect to it, if you plug in here a differential operator that's, again, compatible with the arguments that it's acting on, and taking the adjoint with respect to the residue pairing, it's basically the same as taking the formal adjoint of the operator. So it's very nice. It's a very, very convenient property. And using this pairing and the fact that it's non-degenerate, what you can do is you can prove a lemma that the induced pairing between the kernel of a rational differential operator and its co-kernel on, acting on compatible pairs of Laurent series, and on one side you have the operator, on the other side you have the adjoint of that operator, then this induced pairing is also non-degenerate. Okay, which is, I think, a very nice result. And using that result, you can conclude by referring back to the finite dimensionality of kernels of rational differential operators, you can conclude that the co-kernels also have finite dimensionality by using the non-degeneracy of this pairing. So using this idea, what you can do is you can take a rational differential operator in upper triangular form with Regge-Wheeler operators on the diagonal, and then systematically try to simplify the off-diagonal terms, set them to 0, and if they cannot be set to 0, you can basically, by fully understanding what this co-kernel is, to replace off-diagonal terms by those that happen to be relatively bounded, and this is what I did as part of my simplification. Okay. So there's only basically one more step I want to describe to you. It's the part that came before the simplification in upper triangular form. It is getting to the upper triangular form itself. And I just want to clarify, so how much time do I have left? So if somebody hears me?
Yes, well, 15, 20 minutes.
Okay, so that's plenty of time. Okay. All right, so this part of the strategy basically considers some complicated linear differential equation, and it wants to reduce it through an equivalence transformation to what would hopefully be nicer upper triangular form. Okay. So of course, you can't really do this in a vacuum. So what you need is some initial input about the structure of your original operator. And what you need besides the original operator are the two simpler operators, which would serve as the diagonal blocks, and some morphisms that go along with it. So in the problem that I was working with, it was natural to expect the morphisms to come in these forms, right? So there's a morphism from the original equation to what would be a smaller equation. So it's definitely, this will not be an equivalence, but it will map solutions of this bigger system to a smaller one, as well as an equivalence between this more complicated, in this more complicated diagram. So let me try to explain it. So on one side, you have a new, again, smaller operator, which would be the second diagonal block. So this would be one diagonal block. This would be the second diagonal block. And I would like this equation, all right? So you can see I've extended it by 0 for convenience. I would like this equation to be equivalent to the original complicated equation extended by basically setting the degrees of freedom that appear in this morphism to 0. Okay, so this morphism maps your degrees of freedom into one block, and I want to make sure that when I set those degrees of freedom to 0 in the context of the original equation, that is basically so that reduced more constrained system is equivalent to the system I want to put in the other diagonal block. Okay, but because these two equations are not completely independent in the sense of that they have Noether identities, I have to extend this equation by the corresponding Noether identities, and the equivalence that I want to consider is between this desired diagonal block and this Noether extended original equation extended by some constraint. Okay, so if these morphisms exist, and this second more complicated morphism is not just a morphism but an equivalence in the sense that I described before, meaning that there exist maps going other directions than the corresponding homotopies, then the result of that input is that there exists an equivalence between the original system and an upper triangular system with these operators on the diagonal and some off-diagonal coupling. And this off-diagonal coupling is in fact determined by the structure of the inverse operators and the homotopies that appear in this in the inverse of this morphism. And I will just very quickly flash to you how it's proven. So the way it's proven is basically I compose two equivalence diagrams. So this is one equivalence diagram. This is a second equivalence diagram. Okay, on the left-hand side, I have the original equation that I want to simplify. As you can see, I've extended it by 0 here. On the right-hand side, I have the upper triangular form, that the simplified form I want to get to. Again, it's extended by 0 here. But in the middle, I go through this kind of more complicated system that has Noether identities, which has the original equation. It has the target equation that corresponds to one of the diagonal blocks, and it has this these extra equations that correspond to setting as I said, the degrees of freedom that participate in this morphism to 0, right? And basically, this diagram is the main reason why before I needed to present to you what it means to have morphisms of between complexes of differential equations, because I could not find a simpler way to basically organize the proof than just presenting it as a concatenation of two equivalence diagrams that where at least one leg of them of the two transformations that I'm composing has more than one operator in this complex. Okay. And by the way, there's a whole bunch of notation, some extra operators that have not been defined, but everything in this diagram can be defined by basically referring to the operators that appear in the full equivalence diagram in this between these operators here. Okay, so this is kind of the main non-trivial step that allows me to simplify some original complicated system to upper triangular form. And once I've taken that step, nothing prevents me from basically applying the same strategy to each of the diagonal blocks here. So if the diagonal blocks themselves are somehow complicated, then I can try to apply the strategy to them as well until I have just a fully diagonal system, which in fact does happen in the equations that I was studying in this work and the result that I showed you earlier in the presentation. All right, so the question becomes, so besides this formal machinery of using morphisms between complexes of differential operators, I need to find this input somewhere. So I need to find these input morphisms to do the simplifications. And so it turns out that this is where the literature from the physics literature on these differential equations on the Schwarzschild black hole background becomes useful, because basically the specialness of the equations that I'm studying that allows them to have these simplifications comes from certain hierarchical separation of degrees of freedom that was identified in the physics literature kind of long ago, but not used for these purposes as far as I know until now, right? And this is separation into so-called gauge invariant, pure gauge, and constraint violating modes. All right. So if you look in and you study the physics literature on perturbations, electromagnetic or Maxwell perturbations of Schwarzschild spacetime, as well as linearized gravity or linearized Einstein perturbations of Schwarzschild spacetime, then these concepts are fairly well defined. And geometrically, you can think of them as basically generalizations of well-known identities from Euclidean geometry of the commutations between Laplacian operators and divergences or gradients applied to vector and tensor fields. Okay, so it turns out that when you use this gauge invariant, constraint violating, and pure gauge degrees of freedom, you obtain precisely this kind of input data, right? Up to inverting these transformations, right? So this diagram kind of appears for free by, like I said, by looking at the literature, but making sure that these arrows can be inverted in the sense of morphisms between complexes of differential equations, differential operators, that takes a lot of work. And actually the bulk of the work that I did on this project went into doing detailed calculations and making sure that in fact this diagram has this morphism has an inverse in the different cases that where it was being considered. And the different cases where it was being considered is this simplification of the Lishnerovitz wave equation into gauge invariant modes that obey the spin 2 Reggie-Wheeler equation, and the pure gauge and constraint violating modes that obey the vector wave equation. And studying the vector wave equation independently you can think of it as coming from a certain gauge fixing of Maxwell theory. You can again do this gauge invariant, pure gauge, constraint violating hierarchical mode separation, and then you discover that the gauge invariant degrees of freedom obey the spin 1 Reggie-Wheeler equation, while a constraint violating and the pure gauge degrees of freedom obey the spin 0 Reggie-Wheeler equation, which we already saw in the scalar wave equation case back on the first slide. Okay, and again, I will just want to underline that the possibility of using these this mode hierarchy and completing it to this triangular decoupling does require a certain minor miracle, which I attribute to the specialness of the Schwarzschild geometry, which again has to do with being able to invert the morphisms in this diagram, which heuristically can be expressed as basically saying that the pure gauge system of modes obeys an equation that is equivalent to the one where you take the original equation that you're studying, and then you set the constraint violating gauge invariant modes to 0. All right. So with this input, using the ideas that I showed you on the previous slide, you can do this block triangular simplification and finally arrive at the form of the equation, which can be simplified using this theory of kernels and co-kernels of rational ODEs. And so I think that is basically the last thing I wanted to say. I haven't given you a lot of details on this part, just because I think it will just take a lot of space and time, and it might not be so useful for this audience. But you can of course consult full details in my paper, or you can ask me questions about this at the end. All right. So I described to you a general strategy that can be applied to simplify a certain complicated system of ordinary differential equations using ideas from the category theory of PDEs or D modules or homological algebra. I applied them in the particular case to simplify the equations coming from the separation of variables of certain tensor wave equations on the Schwarzschild spacetime. And in doing so, I obtained results that completed certain previous partial results that were obtained in very trial and error and laborious ways earlier. So once these results have been obtained, so they have been obtained, they can be used for particular purposes, like for example, constructing a green function for linearized gravity on a Schwarzschild spacetime in the particular gauge, which has nice properties from the point of view of theoretic physics. It can also be applied to build ground states in quantum field theory, also using this green function. And perhaps the systematic approach that I outlined for you today could be used to perform similar simplifications on the rotating black hole known as the Kerr black hole, which is significantly more complicated geometry than Schwarzschild. So maybe these tools could be useful there to get around these complications. All right. So with that, I want to thank you for your attention.
Okay, Igor, thanks a lot. Any questions, remarks?
У меня есть небольшое, I have small remark.
Yes.
You use Schwarzschild coordinates, which means
Yes.
that you use derivative by R and T, etc. But you can also try anholonomic coordinate, which means that every point basis is orthogonal and length of the vector is unit. And then the derivatives will be by these vector fields.
Yes.
In this case, your equation will be more close to physical reality because you depend on coordinate system, and coordinate system may be no arbitrary, произвольный.
Yeah.
Maybe
yes,
you
can do this, and some people do this
also.
Yeah. So in my case, it was so the coordinate representation was sufficient and simple enough.
But here length of a vector along R and T is not unit.
But I don't need this to be unit.
Little adjust the derivatives.
Yeah. Okay. Yeah. I agree that you can use this formalism. Yes, but I did not need to.
Thank you.
More questions or remarks? Okay, Igor, thanks a lot.
Maybe I just is
Yes.
it still okay?
Yes,
just to clarify a bit regarding the question or comment which I gave already. So this complex which you used, it's that of linear differential operator, right? Okay. Then it is what is called in more physical literature first quantized Beresty complex.
Perhaps, I like to call it the compatibility complex.
Well, it is the same if it is a resolution.
Well, it's a matter of terminology.
Yeah. And this approach of, for instance, proving equivalence of two different representations of the same equations based on equivalence of these complexes is in fact also known in the literature. I can give you if you're interested. Probably
I used, of course, I used known concepts. So this is it's new in relativity literature. So it has not really been exploited there.
Well, in field theory, for different issues, for instance, I used it a lot to prove equivalences. And of course, it has a straightforward gauge extension. If you just continue instead of
you continue.
you continue.
But the equations I was dealing with are gauge fixed, so they didn't have this extension.
Pardon?
So the equations I was dealing with were gauge fixed.
Well, actually, of course,
they didn't have extension.
I meant pardon to Joseph.
Okay.
Thank you.
Okay, thank you, Maxim. But to my opinion, Igor did not state that he invented this method.
Yes, I definitely did not.
But I also do not object this. I'm just saying that it is in the field theory literature. It is also known. I don't know who.
Yes, but it's, of course, because it's quite a natural approach. Okay, more questions or remarks? Then let me thank our speaker. Igor, thanks a lot. It was interesting. And well, everyone is invited to our next seminar in a week, next Wednesday, the same time. Thanks a lot. Goodbye.
Okay, thank you very much. Спасибо.
See you next week.